So welcome back to our discussion, which will be continuing on laminar flows, and we have been looking at steady laminar flows which are fully developed. So in the last few lectures we explored flows which are in rectilinear configuration. So you have parallel plates, and we were looking at flows which were occurring using Cartesian coordinate system as the representation. So we will look at few problems which where the geometry is no longer describable in terms of Cartesian coordinate, and this is going to be useful in terms of understanding primarily how the governing equations take a different form when you go to curvilinear coordinate system. So the first problem that we will do, so this we have done so far problems in Cartesian coordinate system. The first problem in curvilinear coordinate system that we will do is flow through a circular pipe. So we have looked at the channel flow problem where there was fluid entering from one of the inlets and exiting from an outlet. If we maintain a pressure drop, that drives a flow. So right now we would instead have a pipe which has a circular cross section, and we would have the same driving mechanism. So there is a pressure drop that is applied, and you want to find out what will be the velocity profile due to this imposed pressure drop. The pipe has a radius capital R or diameter, which is twice times R. The fluid obviously has the characteristic properties of density rho and mu, and the length over which we are interested in the pressure drop is given by L. So before we set out solving this problem, we need to understand that now we have to look at a Navier-Stokes equation not in Cartesian coordinate system, but rather in cylindrical coordinate system. So earlier we obviously started out with our governing equation, which was that the fluid acceleration is balanced by pressure gradient and the viscous force, and if there was any body force. So this obviously doesn't change, but we are now interested in writing this down in terms of cylindrical coordinates, and will not be looking into any body force effect. So I'll write this in cylindrical coordinate system. Now if you were to think of the problem in terms of how it is for Cartesian coordinate system, you are saying that okay, I have a component that is r theta z, where the velocities are ur, u theta, uz. So divergence of u, which is the statement of incompressibility if it was 0, is going to now change from what was dou u, dou x plus dou v, dou y plus dou w, dou z, so to derivatives with respect to ur, u theta, uz, and this is where you will start seeing differences coming in, where you have terms that are going to be taking the following form. So you have a term that is dou uz dou z, that is along expected lines. You also have a term that is 1 by r dou theta u theta, but then in the radial derivative you now have a term that is dou ur by dou r plus ur by r. So there is a term that has appeared in our mass conservation equation which is not a derivative, and this is something which is coming about because we are now working with coordinate system where the unit vectors r cap, theta cap and z cap, they are not necessarily constant. Now what do I mean by that? Now they are obviously unit vectors, which means they have unit length. So the length of the unit vector in the r direction, the length of the unit vector in the theta direction, the length of the unit vector in the z direction, they are all going to be unity. So their length do not change. But if you were to just focus on, let's say, the cross section and just look at your unit vector which is r cap and the unit vector theta cap, the magnitude of r cap and the magnitude of theta cap remains the same. There is no change. But then the direction of r cap and the direction of theta cap they are dependent on the value of theta. Because obviously, clearly, if you are to look at theta equals to pi by 2 and theta equals to, let's say, pi by 6, the direction of r cap and the direction of theta cap are wildly different. So, this is to say formally that dou theta of r cap is non-zero. So, dou theta of r cap is actually theta cap and dou theta of theta cap is actually minus r cap. So, you can work this out by writing down the statement for r cap and theta cap in terms of x cap and y cap, and then by taking derivative, because they will depend on sin theta cos theta, and you will actually get that the unit vectors are of unit length, but they are not of the same direction. So, obviously, dou r of r cap, dou r of theta cap, dou r of z cap will be 0, dou z of everything will be 0, and obviously the z cap unit vector is not changing direction, it remains along the same direction. But then the radial and the azimuthal unit vectors, they are a function of theta. Now, this is what leads to you getting additional terms when you start doing this vector operation, because you have to remember this del, which was actually dou r cap plus 1 by r theta cap dou theta plus z cap dou z is now being dotted with ur r cap, u theta theta cap, uz z cap. So, when you do a dou theta of ur, you are also going to do a dou theta of r cap. Now, dou theta of ur is going to give you a term that is dou r, that is going to give you a term that is dou r dou theta r cap, but then dou theta of r cap will give you a term that is ur theta cap. So, when you dot this, you will not get a contribution from here, but you are going to get a contribution from theta cap dot theta cap, which will be the ur by r term. So, this is just to set it up that when you do problems in curvilinear coordinate system, you don't need to necessarily remember what the equations are going to be, but the fact that any derivatives that you start taking of vectorial quantities or tensorial quantities, they are going to give you additional terms. So, when you take a Laplacian, so this is repeating that same point, that if you take a Laplacian of the radial component of velocity, that is not going to be the same as the Laplacian of velocity's radial component. We don't spend time talking about this in Cartesian, but this is a small point that becomes crucial when you are dealing with any curvilinear coordinate system. So, with that, I will write down the Navier-Stokes equation in r theta z, because now we automatically are aware that we will get additional terms in the equation. So, the derivation, you can go through it by writing them down and applying those rules of unit vectors. If you had a body force, you could have a body force in the equation. Del square ur if you write your u theta, there will once again be an additional term and the z component is more or less along our expected lines of what we have already seen in Cartesian coordinate system. So, here the material derivative ddt is dou t plus ur dou r plus u theta by r dou theta plus uz dou z. And del square, the operator, is 1 by r dou r of r dou dou r plus 1 by r square dou theta square plus dou square dou z square. So, here you can see that you will have a term that would be dou square dou r square plus. So, now you can have here an additional term, as you can see, that comes about because you are operating with curvilinear coordinate system. So, the parts that I want you to just focus on and which are purely arising from curvilinear coordinate system. So, you apply a curvilinear coordinate system, and this term, if you are familiar with it, this should remind you of the centripetal acceleration. So, when you are actually writing down your flow in curvilinear coordinate system, there is going to be an acceleration by virtue of the fact that you are moving on a curvilinear track, and that is basically your centripetal acceleration that is there in the problem. So, with all of this, right now we will attempt the pipe flow problem. So, first what we will do in the pipe flow problem is we will list out our assumptions. So, flow through a circular pipe. So, what are the assumptions that we are making? So, the assumptions are that we are dealing with a steady flow and we have fully developed flow. So, steady obviously means that time derivative of all flow quantities are going to be 0. Fully developed means that for the velocity field, any variation, so here it is z is what we have considered, any variation along the flow direction. So, once again reminding you of the geometry, that is my z, this is r, and then you have a theta. So, any variation along the flow direction of flow quantities is going to be 0. We will also make an assumption here, which is a reasonable assumption, that we are going to look at the problem where the flow is axisymmetric, which means all my quantities that I am looking at, they do not have any angular dependence. So, we are looking at an axisymmetric flow that is fully developed and steady. Now, as we have already been discussing so far, that all of these things are assumptions, and these assumptions will necessarily break down as we start pushing the flow to higher and higher flow rates. But at this point, we will work with these assumptions and obtain a velocity profile, and then we will make comments on what is going to actually happen when you are looking at flows that are at a much higher flow rate or higher pressure drop. So, with this assumption, if I go to my mass conservation, I had 1 by r dou dou r of r u r plus 1 by r dou dou theta of u theta plus dou u z dou z is equal to 0. This term goes off because of fully developed assumption. This term goes off because of axisymmetry. So, I am left with this particular term which tells me that r u r should be equal to a constant. My radial velocity should be equal to a constant. Now, the radial velocity boundary condition on the surface of the cylinder or the pipe. So, at r equals capital R, the walls are stationary, which means all my velocity component should vanish at the wall. Radial, azimuthal, axial, whatever velocity components I have, all of them should vanish at the wall because of no slip and no penetration. So, based on no penetration boundary condition, I conclude that UR is equal to 0 everywhere, because that constant should be 0 at the wall, which means it is 0 at all locations. So, this gives me that that constant is equal to 0, which implies that UR is 0 throughout the domain. Okay. So this is what we now have in terms of our mass conservation, that there is no radial velocity in the problem. So let's go to the momentum equation. So in the momentum equation, if I look at the terms, I don't have any radial velocity. So I'm going to cross these terms out. I have axisymmetry, so I'm going to drop that particular term. I'll drop that particular term. And then I'm not looking at any body force, so I'll drop all that term. Then I go back to my material derivative. I don't have any variation along the flow. I have axisymmetry. I have no radial velocity, and I also have steadiness. So each of these terms are dropping because of various different assumptions. So it's important to know why they are dropping, because there are problems where you can have variations of these conditions and you should not necessarily automatically drop them. We saw that in the context of a channel flow with a vertical through flow. So it's important to know that why do you have these terms systematically dropping out. So UR drops out because of the no penetration boundary condition coupled with the other ideas of axisymmetry and fully developed. So which means the entire material derivative is 0 for all the terms. So the left hand side is identically 0 with this assumption. So I'm just dealing with the right hand side, and in the del square operator there is axisymmetry and fully developed. So it turns out to be just a radial derivative. So finally, now if you look at your equation for your pipe flow, you have minus rho u theta square by r is equal to minus dou p dou r. So you have a balance between these two terms, and you have in the azimuthal direction minus 1 by r dou p dou theta, but then I have axisymmetry, so that term is also absent. So because of axisymmetry, this term is also absent, and so I have mu del square u theta mu del square u theta minus u theta by r square. And in the axial direction, I have 0 minus dou p dou z plus mu del square uz. And del square here takes a slightly simpler form. It is 1 by r dou dou r of r dou dou r. Okay. So it's actually a derivative only in the radial direction. So if you were to have an azimuthal flow, some kind of a swirl in the problem, that there was some kind of degree of rotation in the problem, you need a radial pressure gradient to balance this. So what we will do is we will take two problems. So the first one we are doing is flow through a pipe with 0 swirl. 0 swirl means u theta is equal to 0. There is no rotation that is there in the problem. So if there is no swirl in the problem, then the only equation you have to now deal with is the axial momentum equation. So it becomes a fairly straightforward equation. So this particular equation, now if you go back to your earlier statements that if there is no swirl in the problem, so if there is no swirl, then dou P dou R is equal to 0. There is no radial pressure gradient, which means pressure can only be a function of Z. But then the quantity which is the viscous term can only be a function of R, and this can only be a function of Z, which automatically implies that each of those are constants. So, this is basically the same argument that we used in plane channel flow. We are now repeating and recasting it in the cylindrical flow problem. So, we have then 1 by R dou R of R dou U Z dou R is equal to 1 by mu dP dz. Even these derivatives, we should now be writing them as ordinary derivatives. Okay, Uz is purely a function of R, and obviously the pressure gradient is purely axial. Now, this is a second order differential equation with an inhomogeneity. So, the homogeneous solutions of this, so you can see just by either by observation or you can inspect this differential equation, that this has one solution which is a constant. So, Uz equals to constant is a homogeneous solution, and the other homogeneous solution is a log. So, if you substitute for Uz equals to A, this vanishes off. If you substitute for Uz equals to log R, duz dr is equal to 1 over R. So, this becomes R times 1 over R, and that is also a homogeneous solution. So, these are the homogeneous solution. Now, I need the particular solution. So, for the particular solution, what I will have to do is, I will solve ddr of R duz dr. So, this is the particular solution is equal to R by mu dP dz. Now, I can integrate this once and I get duz dr. The particular solution is R square by 2 mu dP by dz. And then I do an integration once more and I get R square by 4 mu. I will write this as del P by L. Now, if I say del P positive, implies that there is high pressure here and low pressure at the outlet, then I can write this as minus del P by L. Okay. So, I am just writing dP dz as minus del P by L. So, I started off from my viscous equations, and then with my homogeneous and particular solution, I arrive at the following as my velocity profile. Now, the time is there for applying boundary conditions. So, you have a pipe which has R going from 0 at the center line of the pipe to R going to capital R at the wall of the pipe. So, one of the boundary condition is that Uz at R equals capital R should be equal to 0. That is a no slip boundary condition. But then you have two constants here in this problem. There are two constants that are there. So, Uz at R equals 0, if I inspect the solution that I have, has a term that is going as log of 0. So, it is diverging, it is approaching minus infinity. So, there is a term which is present at R equals 0 that gives me a logarithmically divergent axial velocity, which implies that my shear stress, which is sigma Rz, that is equal to mu dou Uz dou R dou U R dou Z, those are divergent at the center line. So, I have an infinitely large shear stress or infinitely large velocity if I have this logarithmic term. So, based on that physical ground that we cannot have an infinitely large velocity in the flow, I am going to ignore or I am going to drop that log. So, I will have Uz as A minus del P by L R square by 4 mu. The log cannot be present in the domain, because else I am going to get unphysical velocity inside the domain. Now, with the other boundary condition that uz at r is equal to 0, capital R is 0, I have del p by L capital R square by 4 mu. So, A is del p by L capital R square by 4 mu. So, we are done. We now have our velocity field is del p by L into 1 by 4 mu capital R square minus small r square. So, you have a velocity profile which has a form that is parabolic in nature. So, it has a maximum velocity. So, uz maximum is occurring at the center line. I mean, ideally to find the maximum, you should compute the derivative of the velocity equated to 0 and find the location. But this is a problem which is reasonably symmetrical. So, we are not going through that exercise. But for a general velocity profile, to find the maximum, you should be doing this, finding the location and then basically finding the velocity at that particular location. Because if you remember, for the problem of flow down an incline with a free surface, the maximum velocity was at the boundary rather than in the bulk. So, this is doesn't have too many such surprises. The maximum is at the center line. So, I will just substitute for small r is equal to 0 and I get the maximum velocity to be the following. Now, the argument for dropping the log, which was given by saying that the flow field should not become infinitely large in the domain, you can also arrive at it from a different way. So, the different way to arrive at this is a little bit more tedious from an algebra point of view, but will give you the same conclusion, is if you repeat this problem, instead of flow through a circular pipe where the entire core is having a flow, you have a flow through a circular pipe with a annulus in between. So, there is a region of a pipe inside another pipe and you only have flow through the annular region. So, what that will do is your uz is equal to a plus b log r plus del p by 4 mu L minus r square. You will have one boundary condition which is in the inner region. So, let us call this R1 and this as R2. So, uz at R1 is equal to 0, uz at R2 is equal to 0, which will then give you the constants A and B. You are going to obtain what those constants are, and then if you let R1 go to 0, you will see the log will vanish off. So, keeping the pressure gradient constant, if you then let the inner region, the inner radius vanish off. So, as R1 goes to 0, you will find that B1 will also go to 0. It's an exercise worth doing. It just takes a little bit more time and little bit more algebra, because now you have to actually solve for two sets of algebraic equation, find what is A and B. A and B will be in terms of R1 and R2, and then when you let R1 go to 0 while holding R2 as fixed, you are going to obtain a velocity profile that has no log dependence. So, this is a second way of getting it mathematically. The first way of arguing is that there is no singularity in the velocity field, so the log cannot be there. The other way of thinking of it is that flow through a pipe is the limiting case of the inner pipe going to 0, or flow through an annulus where the inner region goes to 0 and then the log again vanishes off. So, we have now the axial velocity, we have the maximum velocity. Let us find the flow rate. Yes. So, let us calculate the flow rate through the pipe. So, for the flow rate through the pipe, we will have to integrate over the cross section. The cross section is a circular cross section. So, we will have uz r dr d theta. There is no theta dependence in the problem. So, I can take out that 2 pi del p by 4 mu L 0 to r capital R square minus small r square r dr. So, if you go through with the integration, you will have r square by 2 minus r cube. So, that is r to the power 4 by 4. So, you have pi del p by 2 mu L and r square or r to the power 4 by 4. So, your flow rate is del p by L pi r to the power 4 by 8 mu. Okay. So, you have now your flow rate. Now, if you try to find what is your average velocity, your average velocity is the flow rate divided by the cross sectional area, that is pi r square, and you get del p r square by 8 mu L. And if you remember, your maximum velocity was exactly twice of that. So, half of the maximum velocity. The maximum velocity was del p r square by 4 mu L. So, in a pipe flow, your average velocity of the flow is half of the maximum, which is a little different than what you had in the channel flow, where it was 2/3 of the maximum. So, that is just a detail that comes from the geometry. But the interesting bit is how the relation that is that what you obtain in terms of flow rate with your pressure drop and the size of or the cross sectional size. So, in the Cartesian problem that we did, where we are looking at a plane channel flow, it was a cubic dependence on the separation between the two plates. Here it is a quartic dependence, which means if you were to increase your pipe radius by a factor of 2, the flow rate will increase by a factor of 16. So, there is a significant enhancement of your flow rate that you have in terms of your size of your domain. So, now you can view these things in a non-dimensional setting. So, you have u average is del p r square 8 mu L. So, we will take an approach very similar to how we were doing it in a channel flow problem. So, we will start grouping terms. So, let us write this as del p by half u rho u average square, that is a scale of pressure, then r square by 8 mu L into half rho u average square is equal to u average. So, what I did on the term multiplying the pressure drop, I multiplied and divided pressure drop by this particular term, which is half rho u average square. That is basically a measure of my non-dimensional pressure drop. Okay, this is a quantity that we are always interested in measuring, that what is my non-dimensional pressure drop. So, then the term that is left is del p by half rho u average square is equal to r. So, now instead of r, I am going to write this in terms of diameter. So, that is d by 2. So, r square becomes d square by 4. So, that is 32 mu L into half rho UAV is equal to 1. So, this is then del P half rho U average square into d by L is equal to 64 mu rho d U average, which is 64 by Reynolds number based on the diameter. So, you have now a relation that the non-dimensional pressure drop is L by D times 64 by Reynolds number. This quantity is known as the friction factor. So, when you plot this as a function of Re sub d on a log-log scale. So, on a log-log scale, a function that goes as 1 over x will appear as a straight line with a negative slope, -1 slope. So, I am plotting log of 64 by Re against Re. So, it is going to appear as a straight line with a slope of -1. This is what the theory predicts. So, the theory predicts that your non-dimensional pressure drop multiplied by d by L, which is what gives you the friction factor, as a function of Reynolds number is decreasing as 64 by Reynolds number. Now, this ideally means that if you keep increasing Reynolds number. Now, how do you increase Reynolds number? You increase Reynolds number by either increasing the diameter of the pipe or increasing the density of the fluid, decreasing the viscosity of the fluid, or more importantly or more realistically, increasing the flow rate, which increases the average velocity. So, if you keep increasing the flow rate of the fluid, you are going to basically approach higher and higher Reynolds number. So, you go back to your classical pipe flow example. If I am increasing my Reynolds number, I should basically see my pressure drop obeying this particular relationship. But what happens is that roughly around Reynolds of 2000, there is a sharp deviation from this behavior. It no longer obeys this kind of a trend. So, there is a significant immediate deviation that you will actually see from the derivation that we have done in class based on the assumptions, which gives us a laminar flow. Laminar flow basically going back to the assumptions that we made, being that the flow is steady, the flow is fully developed, the flow is axisymmetric, and there was no swirl in the problem. So, with all these assumptions that we made, we had arrived at this laminar flow pressure drop, which says that monotonically the pressure drop is going to be decreasing with increase in Reynolds number. But what you actually obtain is that beyond a Reynolds number of 1000, the pressure drop is significantly higher than what you would obtain from your laminar flow theory. You get a much higher pressure drop than what you would obtain if you would have just used laminar flow. So, the flow beyond Reynolds of 2000 stops obeying the assumptions that you have made. All the assumptions that you have made in the problem of steady, fully developed, axisymmetric, no swirl, all of these assumptions that were there in the problem, all, if not all, most of them actually break down, and you end up getting a flow that is highly three-dimensional, unsteady, and there is significant amount of components that are there in other direction. So, with this you arrive at what would be a turbulent flow where the pressure drop is much higher. And you have to think about this, why this is such a remarkable thing, because the equation continues to be the same. It's not like you are solving a different set of equation. It's exactly the same equation. So, we took these equations, worked out a velocity profile, obtained the velocity profile, and then from that velocity profile obtained the flow rate and all these relationships. So, what we obtained through all of this is known as the Hagen-Poiseuille flow or the Hagen-Poiseuille problem that we have done for flow through a circular pipe. But that flow is not going to be realizable for arbitrary values of Reynolds number. So, if a Reynolds number based on the definition using diameter as the characteristic length and the average velocity as the characteristic velocity, when you exceed a Reynolds number of 2000, the flow that is obtained based on these assumptions, whatever I have crossed out and gotten the solution, that is not going to be a stable solution. So, this is our first encounter of the fact that every solution of Navier-Stokes is not necessarily going to be observed in reality. You can obtain a mathematical solution, which is what we have done. We have basically taken this as a differential equation, made some assumptions, dropped certain terms and obtained a solution. Now, this mathematical solution that we have obtained, the Hagen-Poiseuille profile, this parabolic velocity profile, this is going to describe reality if your Reynolds number was much lower than 2000. If your Reynolds number is larger than 2000, this particular velocity profile ceases to be stable. It becomes unstable. What does it mean? It means that if there was some small noise in the system, both intentionally or unintentionally, like even if you have a flow going through a pipe and you were speaking, even that is a noise, because whatever you are doing, that is basically creating fluctuations in air. This itself could be enough to trigger disturbances, and depending on how sensitive your system is, how far away you are from that threshold of 2000, you can have an onset from that laminar state. And this is why people have taken elaborate efforts of drawing or designing pipes that are extensively long in very, very calibrated condition where noise is eliminated to a large degree, which means you can access this branch provided you have really done a great job in removing any source of disturbance in the system. And that's very difficult. You have a vehicle going past your laboratory, that motion of that vehicle is going to create noise in the setup and trigger an instability. So there are so many sources of fluctuation that is there in your problem. So eliminating those fluctuation is nearly impossible. It's very difficult. So which is why the transition that you will see in most scenarios will occur at Reynolds of 2000. You can delay it, you can push it a little further if you continuously keep making sure that you are being very, very careful about your experimental setup. So you can, another source is that this pipe, if I were to zoom into this pipe, the surface of the pipe is not necessarily smooth. There can be roughness. And nowhere in the picture that we have done here, roughness was anywhere there in your calculation. But when noise is something that becomes important, then the nature of roughness actually starts to become quite important. So the figures that I have drawn here, these are actually dependent on the degree of roughness that you have. The more rough it is, the higher the pressure drop you are going to get. So this is to show and demonstrate not just the fact that you are able to work out a laminar flow problem, but also the fact that all these laminar flow problems that we have derived in class so far, all of these problems can get transitioned to something completely different if there were disturbances that were there in the problem. So with cylindrical flow, we will not be going through a full derivation, but I will just outline another problem which you can attempt using cylindrical flow, which is a problem with swirl. So here you have a radius R1, you have a radius R2. The inner cylinder is rotating with an angular velocity omega 1 and the outer cylinder is rotating with an angular velocity omega 2, and there is a flow in the annular region. So there is no pressure gradient driving the flow here. There is a swirl that is there in the problem, which means if you go back to your equations, if you remember, we had these equations. Now there is no axial velocity in the problem. There is no pressure gradient that is there in the problem, but there is a swirl, which means there is a radial pressure gradient which will balance the azimuthal velocity, but then you are going to look for solutions for which this is equal to 0. And you can work out that ordinary differential equation and you will find that there are two solutions for this. One is a constant times r and the other is a constant divided by r. Now you have seen these velocity profiles. The first one is a solid body rotation and the second one is point vortex. Now if you think a little bit, it is not a surprise that you have gotten this as a solution, because what did you solve? You said the viscous force is equal to 0. Now viscous force equal to 0 when the flow has a swirl can happen if the viscous stress is equal to 0. And when is viscous stress equal to 0? When you have either a rigid translation or rigid rotation. A rigid rotation or a solid body rotation does not have any viscous stress. So that is why you got this term. And for a point vortex, viscous stress is non-zero, but the viscous force is equal to 0. And this again, if you think a little bit, you will realize is something that is not very surprising, because if you remember when we discussed the problem for potential flow, we said del square U can also be written as curl of vorticity for an incompressible flow. And point vortex is irrotational, which means curl of vorticity is 0. So the viscous force is 0. Now this is just kind of confirming the solution. I mean, what you should be doing is write this ordinary differential equation, solve the solution and find what you should find. I'm just trying to say that you can think about that these solutions are also consistent from other grounds, because the differential equation that you are solving is a statement of viscous force being 0. And viscous force can be 0 when the viscous stress is equal to 0, which happens for a solid body rotation, and it is also 0 when the flow is potential, which will happen for a point vortex. So that's the reason why you get these. Now you will apply the boundary conditions in this problem. So you have a u theta that is a constant times r plus a constant by r. You apply these boundary conditions and you will find these two constants in terms of omega 1, omega 2, R1 and R1 and R2. So you can work that algebra out, solve the two equation, because the boundary condition is u theta at r equals capital R1 is equal to omega 1 R1. That's a no slip boundary condition on the inner cylinder. On the outer cylinder, u theta is equal to omega 2 R2. The fluid has to stick to the surface of the cylinder. And so with these two boundary conditions, you can find what the two constants are. And you will find a swirling flow where the fluid is going to go around in a circular motion. Now here again, there is going to be a parameter, just like Reynolds number was a parameter. Here there is going to be a parameter which will tell you the amount of centrifugal force with respect to viscous force. And if you were to do a problem where, let's say, omega 1 was 0 and omega 2 was non-zero, which means the inner cylinder was held at rest and the outer was spinning. So the equivalent to the Reynolds number is a number called Taylor number. And if you keep increasing the Taylor number, at some point this problem is going to become unstable, which means that the base state solution that we derived, u theta is equal to r, this will cease to exist. So again the assumption of steady, axisymmetry, fully developed, all those assumptions are going to break down, and what you will end up observing will be toroidal cells that are stacked upon each other. You can imagine like a stack that you have created. So you have a pole and you have basically put a lot of donuts or vadas on top of each other. So you have these toroidal cells which will start forming beyond a critical Taylor number, and you keep increasing the spin and it will become more and more disorderly. But what is the learning from all of this? The learning is again the same. This is an exact solution of Navier-Stokes equation with the given boundary condition. Just like the pipe flow problem is, just like the channel flow problem is, just like the plane Couette flow problem is. All of these are exact solutions. But these solutions are not necessarily stable for all choices of parameters. Just like a pipe flow problem becomes turbulent beyond a critical Reynolds number, this particular problem of a counter-rotating pair of cylinders, which is known as a Taylor-Couette flow, also becomes unstable. And it's very remarkable in terms of when you visualize this, you will see these flow which looks very homogeneous. There is no axial variation, will develop clear axial variation or clear axial wave number. So that fully developed assumption that you have made, the steady assumption that you have made, those are going to break down beyond a critical value, which is giving you a measure of centrifugal force to viscous forces. Just like in the pipe you had a Reynolds number. So all these solutions that we are working out, we are working them out in the class, but there is also this caveat that these are mathematical solutions which will not necessarily be the stable solutions, which means they will not necessarily be observed in reality for all choices of parameters. So we will be working with these problems and these solutions with the implicit assumption that we are in a laminar regime. So we are not going to go into a great detail regarding what happens post it goes from a transition from a laminar regime, but knowing this fact that there are these terms which based on our assumptions have been dropped. These are nonlinear terms. The terms that have been dropped based on our assumptions are nonlinear terms. You can see there is a u squared term, there is a ur u theta term, then there are nonlinear terms everywhere here. All these nonlinear terms are going to be playing a role in the growth of your disturbance once you cross that threshold, and there will be an onset of an instability. Okay.